said, I am the manager of the optical microscopy core facility here at Notre Dame. Our location, we're fairly centrally located on Notre Dame's campus. Most of our equipment is in Galvin Hall, and that's my contact information for anybody who wants to know. We are part of a larger core together with the electron microscopy, in vivo imaging, and histology cores. We make up the Notre Dame integrated imaging facility. We have a number of instruments available at the core, including light microscopes, wide field and confocal fluorescence systems, as well as some image analysis software packages. Our most recent acquisition to the facility is the Bruker MuVi selective plane illumination microscope, SPIM, or more informally known as the LightSheet microscope. This system was paid for with funds from the NSF Major Research Instrumentation Program and from the Notre Dame Research Office. And this is a top-down view of our system. See if I can get the pointer on. The MuVi SPIM has is horizontal. It has a 4-axis setup with two-sided illumination, and then again, two-sided detection paths. This is optimal for imaging large volumes very quickly, and I'll let Chris kind of expand on this. This system is ideal for imaging embryos, organoid cultures, xenophis oocytes. It's also set up for cleared sample imaging, and it is set up for studies requiring any kind of photo manipulation. We have Imera's software for image analysis and presentation. We've also requested funds to purchase Vision 4D software from Arevis that is generally better at handling large data sets, and it can also be hosted remotely for cloud applications. You can do your image analysis from the comfort of your own home. I'm in the process of setting up a LightSheet microscopy service. I'll provide hands-on training opportunities, as well as an imaging service if your project doesn't demand heavy use of the instrument. And we're also trying to update the infrastructure so that we can provide remote access. Excuse me. So the idea would be that you could access the instrument remotely and send me your sample. I'll mount it on the system, and then you can operate it remotely. So that's the goal within the next month or so, to be able to offer that for members of the CTSI and beyond. And at this point, I will turn it over to Chris. Christopher English is the product specialist for Bruker, and he's going to talk to us a little bit more about the system and the benefits of LightSheet microscopy in general. So let's see. Okay,
I'm sharing my screen now, Sarah.
Okay, great. Thank you.
So thank you for the introduction, Sarah. So that is mostly accurate. I actually just got recently promoted to Eastern Regional Luxendo Manager, meaning that we have been expanding in the United States so well that we're going to start looking for an assistant for me.
Oh, congratulations on your promotion.
Oh, thank you. So that means you will get more access to support services from us. Just to touch on what Sarah said about remote controlling the MuVi. It is, once you understand how it works, it is actually just as easy to use it as if you were in the lab or if you were across the country, like I routinely am when I work on the system with Sarah. As you'll notice here, there's no eyepieces for you to look into. So once the sample is mounted on the scope, it is 100% based use through the joysticks and the computer. So you really don't miss anything by remote use of it. And I highly encourage giving it a try. So what I'm going to do today is do a little background on what LightSheet is and how it's different than confocal and wide field, and then get into a little bit of the nuts and bolts that makes the system that is in Sarah's core unique, and explain in depth some of the capabilities. And then I have a bunch of pretty images at the end. And I did say earlier to Sarah that if somebody brings up a question, we don't have to wait till the end. So with that, introduction slide as to why you might want a LightSheet versus a conventional confocal or wide field system. What everybody wants when they sit down at a microscope is they want to be able to, or maybe not everybody, but folks imaging zebrafish and Drosophila, they want to acquire large volumes of data. They want to acquire quickly at high resolution and gently. However, with confocals, typically large volumes make things slow. And if you use high resolution, then things get dim. So you have to use more laser light, and that ends up killing the sample. But that can be overcome with by changing instruments. And in particular, utilizing some technology that was actually first described in 1903 by a group from Germany with the advent of the ultra microscope, where they have an illumination lens that is perpendicularly set to the detection lens. And in that system, they were able to illuminate single optical planes and take pictures. Granted, that was just a transmitted light scope. It did the job, but was forgotten for nearly a century. Then in 1993, the technology was rediscovered and utilized with fluorescence for the first time. Then 2004 came along, and Ernst Stelzer's group published the very first SPIM paper. And in 2014, Nature named the LightSheet fluorescent microscopy method the method of the year. So what is the real difference between a LightSheet or most LightSheet systems and confocals? That is in where the illumination light comes from. In wide field and confocal, the same objective that does the detection also does the illumination. In many LightSheet systems, however, it is a totally separate optical path that supplies the illumination. In this diagram on the right, the excitation light is supplied by the lens on the left-hand side, and the detection is accomplished by the objective on the right-hand side. So in other terms, the illumination light is selectively illuminating a single plane. And this is where the term SPIM came from, selective plane illumination. So just basic knowledge, LightSheet and SPIM are for the most part interchangeable. I will get a little bit more detailed as to why one might not be a true LightSheet, but really just a selective plane illumination microscope. So in comparing from LightSheet to confocal, confocals illuminate the entire sample simultaneously, with the focus being at a single optical plane. And they collect a number of spots, either spinning disk confocal does this by a rotating disk. The laser scanning confocal rasters across an image. And really, it's just detecting single points that are compiled to make a full image. But the out of focus light, the out of focus excitation light hits above and below the focal plane, simultaneously causing photo damage to the out of focus planes. In comparison, LightSheet supplies the light perpendicular to the detection, so that only the focal plane is illuminated at a single point in time. So if you were to compare these a little bit more over time, the number of seconds that it takes to scan an entire image can be quite a lot. So in this paradigm, to achieve a given signal to noise ratio, it would take a laser scanning confocal about 200 seconds to collect the entire data set. In comparison, the LightSheet system, using different methods, can collect the same volume of data in about 3 seconds. This significantly reduces the photobleaching and phototoxicity. And if you want to just further discuss exactly how you get such a big increase, I'd be happy to go into detail more, maybe on a one-on-one session. But really, the key advantages of the LightSheet compared to the confocal are dramatically reduced light dose, leads to less photobleaching and phototoxicity. Detection of the optical sections is done in one shot, so it's much greater speed, and you're still dictated by the optical physics of the detection lens. So if you were to use an identical objective on a confocal, you would end up getting the same optical resolution. So really, all of these key points make the system ideal for imaging live samples. So hitting on exactly how the LightSheet is created and splitting the true LightSheet systems from maybe a SPIM only system, are these two different techniques. What was implemented in the first LightSheet system was a static LightSheet. And this is created or generated through the use of a cylindrical lens that is put in front of the illumination objective. The cylindrical lens takes a coherent beam and then shapes it into this hourglass shaped sheet. So instead of a Gaussian beam, this is a Gaussian sheet. And this can be sent through the sample and illuminate it, and you can take a very nice picture from it. There are still a number of home-built techniques that utilize the cylindrical lens method to generate the LightSheet. But this is a true light sheet. So at every moment in time, there is a full light sheet passing through the sample. In comparison, what the MuVi SPIM system utilizes is a digitally scanned light sheet. In this system, there is no cylindrical lens. There is just a coherent beam that gets focused through the objective, and the objective creates a Gaussian beam, which is very thin in diameter on all dimensions, and especially in the vertical axis here. So if you were to illuminate your sample with this, you just get a line through your sample. So we utilize a scanning galvo mirror to move the beam up and down in the axis of the image axis and fully illuminate the focal plane. So integrated through time, this does create a light sheet in the sample and on the camera, but an instantaneous moment. There is no light sheet present. It is just a really fast moving beam microscope. So the digitally scanned light sheet systems are selective plane illumination systems, but maybe not true light sheet systems. Any questions there? All right. Moving on. Since so many different microscope light sheet or SPIM systems use the scanned Gaussian beam, I put together this little diagram that kind of shows that you really need to pick the right tool for the job when it comes to utilizing or picking the light sheet system that's right for you. So out in my workshop, I have all of these different saws and they utilize the same blade, but I cannot use them for the same jobs. And that's why I have all of the different types of woodworking equipment. Similarly, all of the light sheet systems shown in this diagram utilize the scanned Gaussian beam or digitally scanned light sheet. However, the samples that they are capable of imaging are very, very different. And this has to do with the objective geometry. And each system not only has different objectives, but different numbers of objectives. The MuVi SPIM system has 2 illumination and 2 detection lenses. InVi has 1 illumination and 1 detection. The QV system has 2 objectives that can either be an illumination or a detection lens. So in principle, it does have 2 illumination and 2 detection lenses, but they are both on the same sides of the sample. The large cleared sample system has 2 illumination and 2 detection lenses, and that is very similar with the TrueLive 3D. What makes the systems even more unique is the specific objectives that are used, as objective geometry and specifications really need to be perfect in order to get a optimal pair of illumination and detection lenses. So you don't end up having objectives bumping each other because the working distances are too short, or the front angle of the physical shape of the objectives are too big for them to be in co-focus. So that makes it so you end up spreading the systems out as to what types of samples you would utilize each system for. The MuVi as Sarah mentioned, has both clear objectives and live sample objectives. It actually has the most combination of objective choices in the portfolio here, and really makes it a Swiss Army knife when it comes to microscopes in the SPIM world. So in comparison to confocal, I'm going to touch on that for a second. The depth of penetration that you can get is dictated by the physical properties of the sample, how much the aberrations of that sample contribute to light scattering or defocus, and basically making it so you cannot see deeply into your sample. In order to overcome this barrier in the SPIM world, with specifically the MuVi, that is why we have the 2 illumination and the 2 detection lenses, which allow the microscope to acquire data sets that are much larger in volume than what you can achieve on a confocal. So really, this is going on in all of everybody's samples, no matter what type of microscope you put it on. And this is a fairly opaque sample that is shown here. Like this would be similar to the liver and spleen sections that I imaged when I was a postdoc. And really, by the time I got 40 microns in, there was no signal there, because all of the signal had been lost to these compounding factors. So if you really want to get any deeper, switching to an system that has multiple objectives would allow you to effectively come close to duplicating the penetration of that. So before we go on, take a pause here, see if there's any questions, and show a cool movie of a zebrafish that was collected during the zebrafish course in Woods Hole a couple of years ago. Any questions? Okay. So Sarah showed a picture of the MuVi SPIM. Here's another view of it, coming from the side view to the top view, and really it's a box with in which the inside contains all of the entire laser launch, the electronics to control all of the motors, and the LightSheet alignment optics and LightSheet creation mechanisms. Once the LightSheet is, once the laser light passes through the LightSheet alignment optics, it is picked up by a periscope and set to the top plate. And all of the action really does happen on the top here. So the MuVi SPIM is a horizontally organized microscope, as Sarah mentioned earlier, for objective illumination. The standard objectives for detection are the Olympus 20X's, although Notre Dame chose a different combination to go with. The detection is accomplished by 2 Hamamatsu Orca Flash 4 cameras. It is the fastest SPIM on the market for imaging 4 views simultaneously, and we can accomplish this at rates up to 200 frames a second for cropped images. Inside the microscope, you can have up to 6 laser lines ranging from 405 nanometer to 785 nanometers. And you do get what we call multi-view imaging without rotation. And I'll get into that in a little bit. Live samples are mounted from below. And there is an optional photo manipulation module, which the Notre Dame system does have. And it is equipped with all of the visible lines that are inside the microscope, plus a 532 ablation laser. The top plate has a bunch of components on it. At the heart of it all is what we call the Luxendo octagon. And this is an octagon-shaped piece of aluminum that has 2 illumination lenses mounted on it, as well as the 2 detection lenses and the associated chamber. This chamber can be heated and cooled through the use of a heater chiller system, and also can be supplemented with conditioned environmental gas. So if you want to do any sort of mammalian work, you can add your 5% CO2 mixture. Moving out from the octagon are 2 10-position filter wheels located on the left and right sides of it. Further out, there are what we call the mag changers, and the mag changers contain 4 tube lenses, which give effective magnification ranges from 0.7x to 2x times the detection lens. And I have a chart that goes over all of the different magnification options momentarily. And then in the back, there are the 2 Flash 4 cameras. This is an older diagram. The cameras have been repositioned on the Notre Dame system. They are, as I mentioned earlier, the Orca Flash 4 V3 cameras, have a 82% quantum efficiency and a 2048 by 2048 pixel array. At full frame, you can acquire a 1 millisecond exposure plus a 11 millisecond camera chip readoff interval, which gives you 80 frames per second at full frame. So as I said before, the LightSheet alignment optics create the LightSheet beams. They are picked up by the periscope and then set up to the 2 illumination objectives located on the front and back of the machines. And they, as you can see here right in the middle, project the light through the sample. And in this little cone right here is one illumination objective, and here is the other. Sitting right in this position is the left detection objective, and here is the right detection objective. So things are pretty tight in there. That being said, you can still get a full millimeter worth of detection range or Z range with this configuration. If you want more, the 16x objectives give you up to 2 millimeters of travel range. Under the hood of the octagon, the chambers look like this. As I said before, it's an octagon-shaped piece of aluminum with everything bolted onto it. So if you want to change magnifications or change from live sample to clearing technique, it is fairly quick and straightforward to switch the octagons. There are 4 bolts that just unscrew and the octagons pop off. If you're using the live sample stages, that would have to be removed before switching over to the cleared samples stages, or the cleared sample octagon. And then there are many choices for the exact configuration of which octagon you're going to use. And it's kind of laid out on this chart. The Notre Dame system has the Olympus 16X and the Nikon 25X octagons, as well as a Nikon 10X octagon for cleared samples. For live samples, the effective magnification range starts from 13.28x and goes all the way up to 50x at 1.1 NA. Then the single cleared sample octagon has a mag range of 7.5x up to 20x. There are a number of other options that you can outfit the MuVi system with. One of them is the Lux Data Storage and Processing Unit, and that is another piece of equipment that Notre Dame has. This is basically a server hooked up to a giant RAID device that is networked to the acquisition computer through two 10-gig copper lines. So you can acquire terabytes of data on the acquisition machine, quickly port it over to the processing server, and do your processing offline. They also have the photo manipulation device. Here at the top is the heater chiller along with the gas mixer. They do not have the dual color detection module at this point in time. So getting into how things work with the MuVi system. The objective on the top, and then this is how exactly we get an extended field of view with the MuVi system, and why it's necessary. And of course, it's got animations that would be useful. Can you see this? Anyone confirm?
Yes, this looks good.
Okay, maybe I should have done this from the beginning. But let's see if the animations work. Ah, there they go. Try something different. All right, so if we are imaging a giant brain, it is going to be held to the same physics that I mentioned earlier with all of the out of focus, scattering, and extinction characteristics of any single photon microscope. So the illumination is only going to penetrate, let's say, halfway into this brain, giving us a field of view that is essentially one hemisphere. So to increase the field of view for these larger samples that the MuVi was really designed to image, a second illumination objective was added, which complements the missing information that the first objective has. So in total, you can create an illumination field that now traverses from one hemisphere to the other hemisphere, effectively doubling the field of view that a single objective system would be limited to. So for imaging large things like Drosophila and zebrafish, this is very beneficial. Then we look at the detection side of things, and the MuVi SPIM has two detection lenses for very similar purposes. As the detection objective collects light, the focal planes closest to the objective are going to be the most crisp, as they have not passed through hundreds of microns of sample and have not scattered to the winds. Meanwhile, the focal planes far from the detection lens are going to be really scattered and in some instances not detectable, which is what you would see on any confocal for a thick sample. So effective Z range on this setup is theoretically half of the brain. By adding the second detection lens in there, we can supplement the missing information and get a effective 2x detection rate, 2x Z range. So what it looks like in cross section is kind of an exploded diagram of the views that you get from the two cameras. So this is really imaging four separate views simultaneously on two cameras. Breaking this down into quadrants, we have the upper right-hand quadrant is formed by the back light sheet in the right detection lens. Meanwhile, the lower right quadrant is formed by the front light sheet in the right detection lens. Similarly, on the left-hand detection objectives, you get images that are formed from the opposite front and back light sheets. This is an exploded diagram, as the two left quadrants and the two right quadrants appear on the camera simultaneously. So we're not taking four separate views, we're actually just four separate pictures, we're taking two separate pictures. That being said, once the data is acquired, it can be put through the Fusion software, which would register in 3D these two separate volumes, and giving a much more detailed image of the entire animal. So what is shown here is a little bit more than that. This sample has been imaged once and then rotated 90 degrees and imaged again. By doing this, we end up with perpendicular volumes, which can be used to supplement each other, and you end up with an isotropic output where the axial and lateral dimensions have the same resolution. In conventional microscopy, axial and lateral resolutions differ greatly, and the lateral resolution is always better than the axial. So one of the benefits of doing this two-sided detection for animals such as Drosophila is that you can see both the say dorsal and ventral views simultaneously of the same animal. As you can see here, things that go on on the dorsal side are non-identical to that on the ventral side. And if this were to be imaged on a wide field fluorescent system or a confocal, this 300 micron thick Drosophila, you would not be able to see both the dorsal and ventral views in this clarity. So the scanned light sheet isn't the only trick we have when it comes to the MuVi. There are two imaging modes that we have on these particular cameras. The first is area mode, where the light sheet will take the start exposure, and then the beam will move from one side of the chip to the other. When the beam reaches the other side, the camera will complete its exposure and read everything out. Alternatively, there is line mode, where the movement of the beam across the chip is synchronized with chip readout. This improves background and suppresses scattering. And to go in a little bit more detail into this is a breakdown of what happens. And like I said before, in area mode, the beam will move from one side of the chip to the other. And in this case, we're taking 200 milliseconds to go across these 2,000 pixel array. Then once it has reached the other end, it's going to read out the entire chip simultaneously. Well, it turns out that during this exposure, each row of pixels collected noise, not signal, during 99% of this exposure time. So each row for about 199 milliseconds was not collecting signal, it was collecting noise. This leads to significant background around each of these objects. In comparison, the microscope can be run in the line mode. And in this mode, we integrate a single row on the chip at any one time. And that is the point at which the beam is directly overhead. So in this diagram, each row is doing a expose, readout, expose, readout, expose, readout. So where in the other paradigm, 99% of the time, the pixels were collecting noise. And this paradigm, 99% of the time, the pixels are actually just off. So they are not collecting noise, and it yields a much crisper, more contrasty image. So what this looks in real life with a real sample can be seen here. So there is this. I was meaning to remove this, as the Notre Dame system does not have the fast axial waist scanning, but this is a technique of shadow reduction that is compatible with the line scan mode, where most other destriping modes are non-compatible with line mode. And in my experience, it's better to have line mode than anti-shadowing. And I can talk about this afterwards, or if anybody else has any questions. But it's just a lingering slide from a previous presentation. The sample mounting for the live samples is from below, and inside the machine there is a 4-axis stage assembly, which will move the same sample up, down, left, right, forward, backwards, and rotate. The main sample holder is designed to hold these glass capillaries that is shown at the bottom of the picture on the far right. And then the sample is suspended in an agarose plug, and that is pushed out a little bit beyond the capillary, and we image the sample directly through the agarose. This is not the only thing that can be put into the live sample holder. I have put cover slips in and other strange things, as I have seen many samples during the demos that I have run. So it's not limited to this. This is just the most easy to illustrate.
Hey, Chris,
Yes.
we've got a couple questions about size limitations, sample size limitations.
Oh, yeah.
One is, what's the max that you can use to do your imaging? The other question is regarding sample requirements and preparation requirements for larger species like mouse or human.
All right. So really, this is a case-by-case scenario. The numbers that are listed here are for the 20x NA 1.0 objectives that unfortunately you don't have. So these numbers are actually lower than what it truly is. The 16x objectives have a stage travel range of about 2.5 millimeters. And there is 6 millimeters in between the lenses. So that is a much bigger area, so you can fit larger samples in and collect larger Z-stacks. The capillary, so the sample holder holds this glass capillary. So you would be limited as far as when you're using this capillary to the internal diameter of the capillary, which is about 1 millimeter across. For samples larger than that, we have a sleeve of FEP tubing that can go on the outside of the capillary. And this is what I commonly use for Arabidopsis imaging, as the Arabidopsis don't like to be shoved into a glass capillary, and it just gets all difficult when you try and image that way. But I use this FEP sleeve and load the Arabidopsis into the sleeve and for imaging the root tip. Then you're limited. If you're going to use this for any other sample, you would be limited by the outer diameter of the glass capillary. This method with the FEP tubing is also good for mouse embryos, as I have a group in Sloan Kettering in New York, which they fill the capillary with matrigel or collagen, and then they use a pair of forceps, I believe, and they stick a post-implantation mouse embryo onto the matrigel, and then put the FEP tubing around that. And the stickiness of the placenta allows it to adhere directly to that matrigel plug. And those grow up to 3 3 millimeters in diameter over the course of a couple of days. Once you exceed this space constraints of this live sample holder, you can utilize the cleared sample stages and objectives to image significantly larger samples. And I can quickly pop back to, or jump forward to show the difference in the sample mounting. These are all cleared samples shown here, but I have used the similar apparatus to suspend live aqueous-based samples. And then as you can see here, the chamber is much greater. The travel range of these cleared sample stages is now on the order of centimeters opposed to millimeters. And the working distance of the 10x objective is 5.5 millimeters. So when coupled with rotation, you could feasibly image something that is up to a centimeter thick with the 10x objective. Did that answer both of those questions, Sarah?
Anybody want to comment? Additional questions?
I will touch on a little bit more on sample mounting in a few slides. Or well, we could skip right to it. Let's skip the photo manipulation. And since we're on the cleared sample system, we can just talk about it now. So in addition to the 4 stages that are inside the microscope, there is a set of 4 stages on the top of the microscope, X, Y, Z, and R again. And as I mentioned before, there is a wide range in magnifications, as in addition to the 10x, there's also a 4x detection lens and a 20x detection lens. The long working distance of this 20x is 8.5 millimeters. The 4x is, I think, 28 millimeters. And it really is a super easy mounting strategy. As shown here, there is a little a rod that gets held in that tower that gets added onto the microscope, the external stage tower. And I came up working with some other researchers. We came up with this sample mounting method where there's a jaw on a dovetail that slides in and out and can just clamp onto the sample. Or this on the right-hand side, this sample was, I think, put onto a magnet. That was a magnet was glued to the top of the brain. And then there's a magnet embedded in the sample holder. So switching out samples is as easy as just pulling one off and popping another one on. That being said, if the appropriate mounting strategy does not exist, through a little bit of discussion with me or your own exploration with some CAD files, you can come up with your very own sample holder. This is a couple of views of the sample holder that I designed with Sloan Kettering. Here's another version that I came up with. We're working with Mount Sinai. And once the CAD files, I mean, I'm happy to supply the CAD files to the existing sample holders with anybody who wants. Once they're modified to your liking, you can just have them 3D printed and shipped directly to your lab. I've been using Xometry as a printout. The print quality is really high, and the sample holders are very resistant to the organic solvents that are used with most clearing techniques. For larger samples, we can set up a stitch and collect many fields of view, and using the image processor on the data server, it can be reassembled. Here's a zebrafish that was collected at much higher magnification than can be shown with this little screen. Another zebrafish. And here is a pair of embryos that were cleared by James Muller at Sloan Kettering. The data set on the left was about 1.2 terabytes. The data set on the right was 600 gigs. Acquisition and processing for these data sets were under 12 hours. Well, I know that it's under 12 hours. I don't know how much, if it came in at 4, 6, 8 hours. That being said, 1.2 terabytes to you might sound like an enormous data set. However, James and I were processing 4 terabyte data sets last week. Just skipping back up, I just wanted to point out the photo manipulation, and then it really does wrap things up. The photo manipulation module on the Notre Dame system is this side module here, where there is a 532 pulsed laser inside the module that is then beamed up to a pair of X and Y galvos that deliver the laser light to the back aperture of the detection lens. And that would either be the 16X and a 0.8 or the 25X and a 1.1 objectives. This was first data from this was first published in this Nature Communications paper in 2015, and then a subsequent publication has come out in just last year, showing exactly how the system works. Here is kind of a splayed out view of a Drosophila that gets wounded and then then heals up. Then moving on, it really is pretty pictures from here on in. So we could go to questions at any time. I know I heard my cuckoo clock in the back go off, so it is past 1 o'clock. This is a cleared femur from the Fernet lab at University of Albert Einstein University. Cleared mouse brains. And then this is the high-res images of the cleared mouse brains. And then we have some data that was collected over a year ago during the demo that I gave on site. So with that, I think I'm going to wrap up as it's getting late. And any more questions, I'm happy to answer.
I have one kind of off the wall question. In your experience, what's the largest sample size that you've been able to successfully image?
In cleared or live situation?
Live, generally.
Oh, I put on a mouse cochlea that was attached to a cover slip. That was a really interesting one.
Mm-hmm.
So we had being that it was stuck to the cover slip, that's probably the largest. And for that, the way that I did that was I cut a slot in the capillary holder, which would, I could stick the cover slip in. And I only used one-sided illumination and one-sided detection for that scenario.
Okay. What was the objective?
It was a 20x.
Okay.
So your system would be better equipped for that.
Yeah.
But you cannot image since it is, and I put the cover slip on a 45-degree tilt.
Okay.
Another thing that I imaged recently was similar, and I just I shot across the front of it instead of imaging, because it was stuck, the sample was stuck to something. But the mouse ear cochlea on the cover slip was the largest thing I put in the live sample chamber.
Okay.
Aside from maybe Arabidopsis, but then most of the Arabidopsis is actually hanging out of the microscope. I have done a corn kernel that was growing some, 10 centimeter long root. But I did that. It was alive, but I used the 10x objective on the cleared sample system.
Okay.
And just to clarify, that cleared sample qualifier that we give it is really just that. It's a qualifier because it's most commonly used, but you can image aqueous samples with that. Here, this is granted, this was dead, but this was aqueous. This is a rather large, it's probably 2 centimeters from end to end. This was a bone dye. So it's not a cleared sample, it's a stained sample, aqueous in nature. But this was collected with the 10x lens.
Since this system has the ability to illuminate using 4 different laser lines, is it conceivable to use all of those at once? And how many can you use effectively?
Oh, geez. Yeah, that's kind of funny, because I was talking with the guys at Albert Einstein, and he misunderstood me when I was explaining how this worked. He thought you could control which laser light would go in through each illumination arm. So you'd have one color on one side and the other color on the other side, and then we could send some light this way and some light to the left and some to the right. But so the microscope and what is possible, if you're crazy enough to build the microscope, what we can do, and then this is what the two color simultaneous module does, is we put a beam splitter at this position and then add another camera. So then you could do 2 colors simultaneous detection on one of the sides.
Okay.
So you would kick on 2 lasers and then you could image 2 colors. That being said, you could also image, and I have done this during the demo for Iowa State. I did not have this model on hand. So I did do 2 color simultaneous imaging by turning on 2 lasers, putting a GFP filter on one side and a RFP laser on the other side.
Okay.
So one camera was detecting 488. The other was detecting 561, essentially. The issue with that is that you have to find a single focal plane where one view is not super scattered or the other view is not super scattered. What they really wanted was something that was superficial, and you couldn't get both colors on the two sides on a superficial view. So that being said, we're getting an upgrade on one of the demo systems when it goes back to get its papers renewed.
Mhm. Is
Then-
there any other questions out there for Chris?
So, Sarah, that being said, you can do two colors simultaneous on your system
Okay,
just by switching two lasers on and separating the,
placing a filter in front of the camera.
oh, no, just unlinking the two filter wheels and putting
Oh, I
different
see.
filters in.
Okay, no more questions. I'll thank Chris for his time and thank you all for coming and participating. If you have any questions at all, please reach out to either myself or Chris English with Bruker. And I guess that's it.
Thank you very much.
Thanks.